All right, so again, there's two forces going on here. So let's draw a picture here. So you got the liquid pushing up. That's your vapor pressure. Because once they turn to vapor, they start colliding, and that's vapor pressure. So when the liquid is pushing up, and then the air pressure is pushing down, usually there's a lot more air pressure than vapor pressure. So if you think of the arrows as the amount, so there's more air pressure, less vapor pressure, we're not boiling. Again, I do everything I can to try and get you to understand the concept, drawing pictures, demonstrations, or whatever to help you, because it's confusing. It is confusing. When it does boil is when we draw the equal number of airs, right? So we have 1, 2, 3, 4, 5. So if we have 1, 2, 3, 4, 5 air pressure, and then we have 1, 2, 3, 4, 5 vapor pressure, when that pressure starts to equalize, the vapor now can start to overpower and become vapor. The liquid can overpower the air pressure and become vapor, which means boiling. But this happens all at once. So now we're boiling. And that's the best way I can show you with like a picture on the board. That's different than evaporating. This does not factor in with evaporation. It factors in only with boiling. We're going to make sure we understand the difference today. So again, when these two forces or pressures are equal, that's when it starts to boil, and then eventually vapor pressure overpowers the air pressure. So this explains why if we decrease air pressure, so again, going up a mountain, if you decrease air pressure, the boiling point decreases because less energy is needed. Make sure you're writing all this down. Less energy is needed for the vapor pressure to equal the air pressure. And again, with the analogy with the doorway. Let's say the tables weren't in the way. We could give Zeke a running start. All right? If it was just Sean and Zeke sprinted at him,
I'll stop.
there's a good chance Zeke's going to get out the door. Maybe not, but the analogy is there's a better chance if it's only one person, so Sean, versus if all of us are jammed in the doorway. Even if Zeke gets a running start, he's not getting out the door. So the point, again, the point of that is if the people in the doorway, that's your air pressure. The more air pressure, the harder it is to boil. So it's going to have a higher temperature. The lower the air pressure, that's like one person in the doorway, we don't need as much energy to get out. Imagine if there's no one in the doorway, just walk right out. So if there's no air pressure, water boils instantly. So I hope, I'm repeating myself. I hope it's making some sense, because typically students have a hard time with this, and they try to just memorize it, but you know how I feel about that. You memorize doesn't mean you learn anything. So the concept here is you decrease that pressure pushing down, or I'm not going to write both. All right, but if you decrease it, you need less energy to go up against it, so that's a lower temp. Where am I? Right here. But if you increase that for a lot of weight on top, think of it that way, you need more energy to push it up. There's so many analogies. Think of bench press. But more weight, you need more energy to push it up. Same, or squatting, or leg press. Anything that helps you understand the forces here is going to need more energy. If there's more force, less energy, less force. So that explains Table H and what we've been doing in the demonstration. Hopefully you guys are with me. Moving on. Everybody got this? All right. While she's getting that down, yesterday, I think it was actually Silas was talking about this. Raise your hand if you've heard the theory that hot water freezes faster than cold water. Hot water freezes faster than cold water. Where it comes in is plumbing. Hot water pipes will freeze before cold water pipes. So like if you if it's like sometimes it gets like down to negative like 10, like the actual air temperature is negative 10, and people's pipes are usually in the basement. And if the basement gets very cold, or if you have an external pipe like outside the house, it can freeze. A lot of times hot pipes will freeze before cold pumps. So then people the misconception is hot water freezes before cold water. That is completely false. If you took 2 ice cube trays, and you filled up one ice cube tray with water that was like 90 degrees Celsius, and the other one, and it was 5 degrees Celsius, and you put them both in the freezer, and you could see it. Maybe it was like a clear, whatever, freezer. That'd be kind of cool. The one that's at 5 degrees would freeze extremely fast. The 90 degrees would take a long time to freeze. It has to go from 90 down to 0. It has to lose all that energy. So why, or what's this misconception, hot water? I got in an argument with a plumber, actually. I was at my buddy's house. Same guy I went to trick or treat last night. This was in college. I was visiting him in college. It was his apartment, whatever. And just so happened, like, a plumber was coming to do some work. And I wasn't a chemistry teacher yet. I was studying chemistry, whatever. And I got in an argument with the guy. He's like, yeah, hot water freezes before cold water. And I'm like, I should have just left it alone. I'm like in the living room. I couldn't even see the guy. And I'm like, that's not true. And he's like, what? Hello? And I came out, and he's like, well, the hot water pipes freeze before cold water pipes. I'm like, okay, but that doesn't mean hot water.
Why do?
Right. So let's talk about that.
That's not true.
If you fill up a glass with like hot coffee, let's say, like forget a mug, let's say a glass, and then you take a exact same glass and you fill it up with tap water, and you carry them outside, and it's winter time. Which one's going to form condensation first, do you think? The hot. Think about when it's really, really hot and you're drinking something really, really cold versus something that's not as cold. There's more condensation the colder it is on a hot day. It's the same thing in the wintertime. So the hotter the water, the more condensation the container will have on a cold day. Does that make sense? The condensation freezes, and then the pipe can crack. The water inside doesn't freeze. It's the condensation on the outside. That's what freezes. But that's exposed to the air. So that's the misconception of hot water freezing before cold water. That doesn't make any sense. It has to lose so much more energy. I'm going to tell you a really practical thing about this. In the South, farmers who grow fruit, sometimes there's frost. Even deep in the South, sometimes frost happens in the winter. They're still trying to grow oranges, let's say. So what they will do to protect the oranges is spray them with water during the day or just before night. And then overnight, it gets pretty cold, maybe a frost. What happens to that water, that mist on the orange? Freezes. But guess what doesn't freeze? The orange. It protects the orange. Now it's different than a pipe, right? Pipes are metal, and if it's old, it can crack. The orange has the skin, so the inside should not freeze. That's actually what farmers do. And that's the same principle of what I'm talking about. It is relevant. It's relevant to what we're learning about, actually. Gaining energy, losing energy, forces of attraction. So, question?
Well, so you know how people sometimes take boiling water in a pot and, like, if it's really cold outside, throw it outside so if it like freezes or whatever?
Yeah.
So you're saying if you take a boiling pot of hot water and then take a like room temperature one, the hot one won't freeze faster than the cold one?
Right.
Okay.
But then how does that thing work?
Yeah.
If
When
you
you throw both, they'll both do it, right?
How does what work?
If you take like a pot of boiling water, and then you go outside like the winter time, and you throw it and it comes to smell.
Yeah. Well,
Yeah.
that's
Right.
room
What's turning to
temperature.
smell?
Water.
The vapor.
Oh.
It's all about the vapor and the condensation. If you were to, so you're changing the scenario there. If you took a bowl or a pot of boiling water and a bowl or a pot of tap water and just put them outside, the top of the hot water where the vapor is might freeze like pretty fast, but the entire container of water will not. It has to lose too much energy. Now, there's a small chance I'm wrong because I've never done that. Because now that you got me thinking that maybe because of the extreme temperature difference, it loses lots of heat very quickly. But I'm still gonna say no on that one.
Or just do a demo in winter.
All right. Well, remind me. But that's part of that's the deal there. Moving on. All right. Interesting stuff. I think that's interesting. Alright. So, what is evaporation? If we understand boiling now, what is evaporation? What happens when a liquid evaporates? How is evaporating different than boiling? That's what I'm really asking. Take a second to think. I'm going to give you guys a minute. Think about it. How is evaporating different than boiling? I'm done with this. We'll continue. That's about it. Alright. Kara, what do you think?
When a liquid evaporates,
Want me to help you a little bit? So imagine you have boiling a beaker of boiling water next to a beaker of water just sitting on the counter, on the table. So you have boiling water, which you see boiling and vapor, lots of vapor, and then when it's sitting there, you never really see anything. So, but it will. Does everyone agree if you have a beaker of water sitting here, it'll eventually all evaporate? Might take like a week or so, but okay. So what's the difference? Any difference that you can think of, imagining that scenario. No wrong answer here.
the more vapor, or the higher the temperature, it like evaporates faster.
Good. The higher the temperature, it evaporates faster. I like that. Let's write that down. The higher the temperature, the more a liquid evaporates. Good. Higher the temperature, the more a liquid evaporates. I like that. Cal, you have the hook there. Bella, what else? Another difference between boiling water and water just sitting there evaporating. I'll give you a hint. Where are the particles in the water evaporating from? Get the water. No, like where in the beaker? So if you have a beaker and you have liquid, you have water, where are the particles evaporating? Where in that beaker? On top. Very good. So the surface particles are evaporating. Let's write that down. Evaporation occurs at the surface. At the surface. She seemed to just know that. I didn't tell her that. Does that make sense to everybody that evaporates at the surface? Tell them why. How come the ones at the bottom can't evaporate? It's pressure. What do you mean? Explain.
Like, it's not to go from like the bottom.
Why?
The top ones have to go first.
Why?
Because the top ones have pressure on the bottom.
Okay, the top ones are pressure on the bottom. Okay, good, good. What else? What is the bottom? What are the bottom particles not exposed to?
Air
The
pressure.
heat.
No, there's no heat. It's just sitting on the counter.
Air pressure.
Yeah, the air, right? So if a liquid's going to turn to a vapor, where's the only place it could go? Into the air. If it doesn't go into the air, then it's going to stay liquid. We all agree on that? So evaporation occurs at the surface. What holds liquids together?
Force of attraction.
Force of attraction. Shaking hands. So these particles at the surface are attracted to particles below. And then the ones below it are attracted to the ones below that. So the particles at the bottom and in the middle have forces of attraction on all sides. So again, let's use the analogy of the doorway, or think of an elevator. Elevator is a good one. If you're in a packed elevator and you're all the way in the back, and then the doors, there's like 2 or 3 people in front of you, and then there's a door. You can't get out. This is what you said. I can't, if I'm in the back of the elevator, I can't get out until the other people go out first, right? I mean, you could be a total jerk and be like, whatever, and start pushing people. Who doesn't, right? So that's the same concept here, that they have to wait for them to evaporate. So as this liquid evaporates, these go first. Well then, the new surface is now down here. And then those evaporate, and then the new surface is down here. But really what's happening is the particles in the liquid, not at the surface, have much more forces, pressure, she said, holding it as a liquid. The ones at the surface have less forces. So again, with this drawing, look up here. Up here, there's no liquid particles attracting to the surface. So if you think about it this way, the surface only has forces pulling it down. The particles in the middle, they're getting pulled all every direction. Okay? So again, like think of Sean and Kara, you guys in the front. There's nobody in front that could grab you. Okay? Nicole can grab Sean, Sean can grab you guys behind them could grab onto them. That's kind of what's happening. And then you can grab Nicole, Emma can grab some. So people in the middle can be grabbed in different directions, and then they really are on lockdown. They can't move. So the surface evaporates first due to less forces of attraction. Due to less forces of attraction. That's what happens when a liquid evaporates. So what happens when a liquid boils?
It just does it faster.
Yes, it does it faster, and all the particles can evaporate. If you ever really watch something boiling, where are the bubbles coming from? Bottom. So when you boil, particles at the bottom can actually evaporate first. That's like the jerk in the elevator. Because you're giving it so much energy, and those pressures are equal, the liquid doesn't really know what's going on, so all of them try and get out. When you boil, all of them get out at once. We don't need to necessarily write that down. But boiling is when this happens all at once, not just the surface. Evaporation is just the surface, and it's a slower process. Hopefully that makes some sense. Last thing, I really want to do that demo. The demo takes like a minute, so we should have time. Why is boiling and evaporation a cooling process? So forget the vacuum chamber, forget Mount Everest, forget that scenario, just normal boiling point in this room. You put a beaker of water or a pot of water on a stove at home and you boil it. You're giving it heat. How in the heck can it be a cooling process if you're giving it heat? Here's what I mean. When it's boiling, when the liquid's boiling, how is it a cooling process? I told you the other day, I don't remember. Well, when we sweat, it's the same process. When we sweat, sweat's evaporating off of us. How is that a cooling process? It's taking the heat from whatever it's touching away. So, you guys ever spill or have acetone or alcohol spilled on your arm or hand or fingers?
Yeah.
Anybody? What's it feel like? It's really cold. I would show you, but it's really not good to just straight up pour chemicals on students. So, if you put your finger, maybe I'll let you put your finger in some acetone tomorrow. If you put your finger in acetone, it feels so cold. It's immediately evaporating off your skin. And when it evaporates, it takes the heat from your skin. So it feels really, really cold. That's why. So when liquids boil or evaporate, it takes, the vapor takes kinetic energy, because that's what temperature measures, average kinetic energy, takes kinetic energy away from the liquid. And this is actually another part of this. So a boiling liquid will, actually not will is not a good word, cannot, capitalize and underline, cannot, a boiling liquid cannot increase in temperature. Once it reaches its boiling point, that's it. The temperature will never go above that. Whatever that is, if it's 100 degrees, 55, whatever it is. If the liquid's boiling, any extra heat you give it goes with the vapor. So the liquid's temp stays constant. The next lab we do, you're going to see that. All right, let's try and squeeze this in. Can you stop that first? You guys all need glasses.